developed. In fact, the development of electromagnetic waves and some experiments in which people were successful in transmitting electromagnetic waves wirelessly from one point to another during the last 2 decades, or maybe you can say it is during the last decade of the 19th century. That was basically a milestone in communication engineering. And in fact, the whole scenario actually changed after that. You can understand. Means before that, since it was only telegraphic communication, that also over some conducting lines, that was a line communication. Even telephone was also line communication. So it was not uh, easy to do long distance communication. Not only long distance, means in fact it was almost impossible to do intercontinental transmission. So that was a big hurdle before that decade, the last decade of the 19th century. People were not able to do long distance transmission. So communication was actually the handicap that time. So only when people were able to do this long distance transmission wirelessly and using this electromagnetic waves, that was only possible using the electromagnetic waves. So that was a milestone, and then only the communication had a, you can say it was a big jump in the communication engineering. Okay, and as I said in the last class, that the main contribution, in fact, the pioneer in this field was one Indian scientist. Although that time people uh, didn't know that he had so much of contribution behind it. Only people that time thought that Marconi is the person behind it. Okay, so accordingly, Marconi was given the full credit. He got his patent. In fact, he got his Nobel Prize also because of this. Okay. However, later on, it was found out that he actually used the work that was published by Sir Jesse Bose before, in fact, 2 3 years before him. Okay. Anyway, so once this electromagnetic wave was developed and people were successful in transmitting it wirelessly, then this radio system, radio communication, and all these things started developing. Okay? People were trying to transmit data over, transmit message over wirelessly. We'll see afterwards how this transmission actually takes place over the wireless medium. Okay. So today actually we'll just go back into two things that before this last class, I was talking about the telephone system and the telegraphy system, where I said that conducting wires connecting the receiver and the transmitter that used to be used for transmission. So now one question comes that is it that the this electromagnetic wave, is it only possible to transmit it wirelessly? This is in space. Is that the equation that we developed in the last class, that equation was basically developed for free space, transmission of electromagnetic wave in the free space. And in fact, the physicist, through their equations and all these things, that started with Maxwell, he used all this mathematical formulation and all these things, and then he uh, was able to make a idea. He was able to propose that it is possible to transmit electromagnetic waves in space, free space. Okay, and later on Hertz, then Tesla, then Jesse Bose, Marconi, Popov, all these people then used the started from his from that point, using his mathematical idea, Maxwell's all these equations. They were able to develop the electromagnetic transmission system. So it was mostly that time it was wireless communication that they were working on. They were trying to think of how to transmit electromagnetic wave wirelessly. Okay. Now, since there was also line communication, and in fact line communication was used, was still there, and in some places wireless instead of wireless communication, actually it is better to have wired communication. Okay, where you should have the direct connecting path between the transmitter and the receiver. So then people also started thinking that whether it is also possible to transmit this electromagnetic wave over a guided medium. Why I am saying guided medium? Because see, when I am transmitting the electromagnetic wave wirelessly, I am have once I throw it in the air, once I throw that radiate that electromagnetic wave in the air, I don't have control over it that it should reach at some point. So it's not a point-to-point communication. Okay, you cannot have it directed only in one point, from one point to another point. So it is somewhat like you are throwing it in the air, and so your receiver has to catch it from the air. Okay, anyone in the space can catch it. Actually, your signal can be received by anyone at any point. Okay, although some directivity is possible, it's not that you have to transmit the EM wave 360-degree all around. It is also using some directed antenna. You can always focus your electromagnetic wave in a particular direction, but you still cannot have a exactly point-to-point communication. You can direct it towards one direction, but still it's not possible to have it exactly that it will be from one point to another and no other person should be able to catch it. It's not possible. Okay. So in some cases, it was also required that it should be a point-to-point communication also. So people have also thought of that whether this electromagnetic wave, whether that can be transmitted over some guided medium where the electromagnetic wave will be guided along a conducting path only from one point to another. Okay, it will not radiate all around. Okay, the wave should not, the message should not radiate all around. Okay, so accordingly, different yeah, the medium people were started, they started to work on, and two types of guided medium we can talk about is the transmission lines and the waveguides. In fact, the wired communication, that line communication that we have talked about, the telegraphy system and the telephony system, they were basically transmission lines. We have already talked about to some extent the transmission lines. One addition to that is the waveguide. Okay, so these are the guided mediums. Okay, first we will talk about the transmission line. So as the name suggests, you can understand what is a transmission line. That it is basically a structure or a conductor that will be transporting the electrical energy from one point to another. Okay, and that is what we were doing in telegraphy. That is what we were doing in telephony system. So a transmission line will be consisting of two conductors separated by a distance. Okay, that a twin pair we have talked about, coaxial cables and all these things we have already talked about. So it is basically a pair of conductors that will be connecting your transmitter to your receiver. So when an electrical source you have it at one end, obviously it will energize the conductors, okay, and that electrical energy will be flowing along the conductor. So that is how the transmission line works. So it is just like a simple conductor. Now these are the different structures, different types of transmission line structures that you may have. One is the coaxial cable. I have already briefly discussed about it earlier, that what is the coaxial cable. Okay, parallel line, parallel wire transmission line also I have briefly discussed earlier. So these are very common. Okay, this microstrip line, this is what something new to you. This is nowadays you will see it in many of these. In fact, your mobile phone is also having it. Okay, so all these electronic gadgets where you have to have some transmission of the EM wave from one point to another. In fact, in your mobile phone, you have to have the signal. You catch that signal. You have one antenna at one point in your mobile phone. Okay, that signal has to flow through your in the mobile phone itself. In the mobile phone itself, it has to flow, and it has to go to different parts of your mobile phone circuit. Okay, and that signal is of very high frequency. That signal that you catch in your mobile phone, that is of high frequency. So if you just use simple copper wire for connecting different parts of your mobile phone to transmit the signal inside your mobile phone itself from one block to the next block, okay, say from antenna it has to go to a power amplifier, then from power amplifier it will go to one oscillator, then it will go to one filter, then it will go to your speaker, like that. Okay, so it will, that signal has to flow from one point to your speaker ultimately. Okay, that flow of signal will be inside your mobile phone itself. Okay, but that signal is of high frequency until it is you do the down conversion to audio level. Okay, it will be of very high frequency. That way you will understand afterwards that how the down conversion takes place. So that signal is of high frequency flowing inside the mobile phone, and that connection cannot be a just simple wire. If you just use the simple wire that you use for your connecting different electrical equipments at your home, that copper wire or something cannot be used for it. Okay, then there will be a high attenuation and you will not able to hear something. Not only attenuation, it will pick up noise also. So it has to have some special arrangement. Special type of transmission line is required for transmission of this high frequency signal inside your electronic gadget itself. Okay. System is having a printed circuit board, PCB. We call it PCB. PCB is there and all the electronic devices are basically mounted on that PCB. Okay, it is mounted on that PCB, and one device on that PCB has to be connected to another device through some line. Okay, there should be a conducting path connecting one device on the mounted on the PCB to another device on the PCB. I think you have seen some PCB and all these things, you must have seen it. Okay, so these conducting wires in your in that PCB, they are all microstrip line. They are microstrip line. Okay, because this PCB is designed for handling high frequency signal. So it cannot be just copper connection, copper wire connection. Okay, it cannot be connect. All the connections cannot be just coppers. Okay, it has to be of special type, which are called microstrip lines. Okay, so that is what you have in your PCB, this microstrip line. Okay, so microstrip line, it is already written there. It is a thin metallic strip on one side of a dielectric substrate, and on the other side you don't have any VA. So it actually you are forming the pair of conductor. You are forming it by having the ground on the other side of the PCB. You can see the picture here. I have shown it that the PCB is basically is the printed circuit board. The board itself is basically a dielectric material. It is made up of some dielectric material, and on that PCB you do the etching. It is etched, means you do some etching processes there to make your PCB circuit, PCB design and all these things. So you do etching, form the conductor on one side of that PCB, and on the other side you have your ground. Okay, so you have that actually forms a path, that forms the path of transmission. Okay, so this is how the microstrip line actually works. Okay, in this microstrip line, the fields are actually confined in between the conducting that metallic strip, conducting strip, and the ground below it. So basically, it is confined in the dielectric slab. So the electric field will be in between these two. Okay, and as I have written, it is used in printed circuit board for high frequency handling, high frequency signals. Okay. Next, this unbalanced line. This also I have mentioned earlier. Unbalanced line, that in, when I was talking about telegraph, I said that only one wire will be connecting from the receiver, from the transmitter to the receiver, and at both ends you have a ground. Okay, we just connect them to the ground. So basically it is a single wire connection. Okay, but this will be obviously unbalanced. Okay, now what do you mean by sorry, mistake here, type equation here, that will be deleted. Okay, if two conductors are symmetric around the ground, then the line is called a balanced line. Okay, then the line is called a balanced line. Otherwise, the line is called unbalanced. So if you see here, this is a balanced line. Okay, this is a, with respect to the ground, I have both the conductors having the same potential difference with respect to the ground. Okay, one will be plus B, the other one will be minus B. Okay, if that is the case, it is called a balanced line. Okay, whereas actually this dielectric slab, even the coaxial cable, because coaxial cable actually this outside is having it is having a potential difference with respect to ground, but inside one is actually having the field with respect to the surrounding conductor. Okay, so it is also unbalanced. This is unbalanced, this is unbalanced, this is unbalanced. These are all unbalanced. Okay, so coaxial cable, microstrip line, and that single conductor line, they are unbalanced lines. Okay. Now, when I do a transmission, it is quite straightforward. You can understand that there will be some delay because there is some finite velocity. Okay. Although that velocity is of the signal, that electromagnetic wave, whatever is transmitted over this transmission line, although that one is of very high speed, the speed of light, okay, but still there will be some delay in when I transmit one signal at this point. The time it takes to reach the other point is given by L is the distance. So L by C, that will be the time it will take. This waveform will take that much time to reach the other. And this this TR can be accordingly written as L into capital T. Capital T is the time period of the transmitted signal. Capital L into T by lambda. You can see how I have written it. It's straightforward. So now you see that there is a delay, and this delay I will like to have as small as possible compared to the time period. That means, suppose I initiate a signal here, I will like to have, ideally, I will like to have exactly that signal to be appearing at this point without any phase delay. That is what I would like to have. But obviously there will be some phase delay due to this TR, this transmission delay. There will be some phase delay between the signal here that you initiate here and the signal that is reaching here. Okay, it will take some time. But I will try to have this one compared to the time period of that signal. I will try to have this delay as small as possible. Then it will look like as if the signal is more or less reaching the load at the same instant. If my TR is very, very less compared to the time period, that means within that same waveform, okay, within the same time of that waveform, within that wave, this one, there will be a delay, but very, very small compared to the time period. I think you can understand this. That if we can have something like this, because we cannot make this one equal to 0. If we want to make it 0, then C has to be infinite. That is not possible. Okay, C is very large but not infinite. So we like to have this TR as small as possible compared to this time period T, which means that if this lambda is large, okay, if I make this lambda very large, okay, then this TR will be very small, okay, compared to this capital T. Okay, in other words, you can also say that I will like to have very small frequency. F is small. If F is small, T is large, lambda is large, okay, and then you will be having this TR, okay, this TR will be coming out to be smaller. Okay, so that is what we will try to. We will always like to have that. Okay, that means if it is a low frequency signal transmitted over this transmission line, I will not have much delay in the transmission. It will as if that the signal is reaching at the same instant of time. The signal is reaching the other point. But whenever the frequency of the signal is increased, then you will see that this delay becomes a bit significant. It will become a significant when this frequency is higher and higher. When the frequency is higher and higher, then you will be having this T, capital T, smaller and smaller, and hence this delay will be then prominent. Okay, and that is actually not desired. So that is one problem with the transmission line, that transmission line cannot be used for a very high frequency. It is generally used for low frequency. Electromagnetic wave of low frequency is transmitted using transmission line. So that is the problem. We will also see that there are other problems using transmission line. So it is used, but it is used only at lower frequencies. Now it is not used for very high frequencies. What are the other problems? Let us see. As you know that when current is going through, flowing through a conductor, there will be magnetic flux and all these things will be produced. So the conductor has some inductance. The conductor is always having some inductance, whatever, how much ideal it is, but it is not, it cannot be exactly ideal that there is no conductance. Practically all conductor, they will be having some resistance, they will be also having some inductance. Okay, and that inductance, we can assume it is not concentrated at one place, it is basically distributed along the whole conductor. Okay, similarly the resistance of that conductor is also distributed along the length of the line. So there is resistance, there is inductance. Then when I am using two conductors, or even when the conductor is there and the ground is there, so between these two conductors, okay, they act like a parallel plate capacitor. You have studied parallel plate capacitor, so you know. So here when there are two conductors, okay, then either two conductors or one conductor and the other one is grounded, okay, ground. So you will be having some parasitic capacitor formed between the two conductors, which will also offer some capacitance. Okay, that capacitance will come in between the two conductors. Some capacitance effect will be coming. And again, this capacitance is also not concentrated at one point, it is distributed along the length of the conductor. Also, the medium separating the two conductors, ideally that should be a good insulator. But suppose it is not so, there is some leakage. Say, for example, when it is a humid condition, two conductors are there and it is a bit humid condition, then there is some amount of current that will be leaking from one conductor to the other. There will be some flow of the current from, although that is very negligible, but there will be a flow of current from the positive conductor to the negative conductor through the air when it is humid. So there, that separating medium between the two conductors, that may not be exactly a good insulator. So there may be some conductance between the two conductors. So that can be, now we can model it like this. This is the modeling, that I have inductors, resistance, like that along the transmission line. Okay, this is how I am modeling. And the capacitor, as I said, the capacitance will come in between the two conductors. So this is the capacitance effect, I am modeling it. And this is the conductance between the two wires. So I can model my transmission line in this form. Okay. Now, when voltage is when you try to yeah, you have some source connected here, then current will be flowing through it, and when current flows through it, then there will be some voltage drop as the current flows across the transmission line. There will be some voltage drop. Okay, and this voltage drop with respect to the distance. Okay, so this is the del v del x. Okay, which I am writing as dv dx as del x tends to 0. Okay, so this is that drop in voltage when the current is flowing along the conductor. That will be equal to drop, since it is drop with respect to dx, the v will keep on dropping down, so it is minus r plus j omega l. I think this you know, j omega l is the impedance offered by the inductor. So this is the total impedance, resistance plus the reactance offered
What is
by
J?
j is the root over -1. Okay,
Iota.
which I think in maths you use it as I. Okay,
Okay, sir.
see now from now onwards in electronics and electrical engineering we will be using J. The reason is that in electrical and electronics I actually is used to denote current. Okay, so in mathematics you have studied it as I. Okay, but the problem is there will come when if you use I in electrical or electronics. So that's why in electrical electronics course we always use J. Okay, so keep it in mind that J is the same thing that you have studied in mathematics. There we write it as I, but now onwards we'll be writing it as J, so that we don't confuse it with current I. Okay.
Okay, sir.
So as you know, impedance is basically a complex number. Okay, resistance plus the reactance. The reactance offered by the inductance is given by j omega L. Omega is the 2 pi f frequency. Okay, so that impedance into I, this will be your dv dx. Similarly, di dx is the current that will keep on reducing. When if the current is flowing, there since there will be some leakage due to this capacitance as well as this conductance, this will be the parallel path. This is the parallel path that offers some leakage current, and due to that the current will also flow, will reduce in this way. Okay, this is just as you know, there is a parallel path how to calculate the current flowing through it. The current will be equal to the conductance G plus j omega c is the admittance. Okay, so this gives you the admittance. The total admittance of this circuit is this admittance into V. Okay, so this is the equation basically governing the transmission line system. Anyway, just in this context, let me tell you, I am in my slide, you will see there are many mathematical equations just written for you to learn it. In your exam, I am not going to ask you all the derivation and all these things, because these things you will be studying in details later on. Okay. So this is just a basic course. So I am not going to ask you any mathematical derivation. Just small things, small very basic things I may be asking. Okay, so you need not to bother about all the derivations and all these things. I'm just giving you the snapshot of some of the results, so that you at least understand mathematically also that how things are working. That's what. Okay, so don't
Sir,
ha bolo.
sir, can you please explain what is admittance?
Admittance is just the inverse of your impedance. Say, as if you don't have any inductance or capacitance, then we say one is the resistance. Any conductor is having resistance. That is the basic thing you know. And the inverse of resistance is your conductance. Okay. Now, when you have inductance, then the impedance actually is R plus j omega L. Okay, here in fact actually there will
Sorry,
be
sir. So
R.
could you please repeat? Someone removed me from the meeting.
Huh? Someone is removing you from the meeting.
Yes, sir.
I think you
So if
should
you
make
make everyone
everyone attend.
attendee, then they won't be able to remove.
Okay, then just a minute. How to do it? Can tell you. I think somewhere here I have to do it. Make an attendee like that. But that means I have to do it one by one
You can do from top.
from top.
Yes, sir.
Sir,
Sir,
in
about dismiss.
participants option.
This one.
Yes, sir. Click it.
Then
Sir, manage
manage
permissions.
permissions. Okay.
Maybe it's there. ये कहीं और आ गए.
I'm not sure whether. Acha. Today's lecture. Who can bypass the lobby? Always let callers, announcement callers who can present, allow mic attendees, allow
Sir,
camera.
present, I think.
Huh?
Who can present?
Who can
Lobby, who
present?
can present?
Acha,
Yes.
this one, huh?
Only me. Only
Mm,
me.
only me. Acha.
Sure.
Okay, thank you. So I think this is done, nah?
Yes, sir.
I think this is done. Okay.
Sir, can you explain? Do we take real part in this limit?
Huh?
Sir, do we take real part, that is R and G only?
R? No, 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 no. We don't take R only. We take j omega L also.
So
See,
why we are taking imaginary part?
huh? Okay. I think you have studied to some extent anyway. I'm telling you. When you have any conductor, in the conductor you will be having R, you will be having L inductance, and you may also have capacitance. Okay. Resistance is there. It will, you know that there will be some drop Ri because of the Ohm's law, that you know. Okay. Now this inductor also gives you some effect, but there will be no voltage drop due to inductor. What it will do, it will actually change the phase of that voltage. Okay, it will change the voltage. That means the voltage, when it goes through a pure resistance, there will be no voltage, yes, phase change in the voltage. But whenever there is an inductor, the voltage and the current, they will have some phase difference. I think this you have studied earlier, na? That
Yes, sir. Sir, we have studied this, but we have not
so
studied
there
this
will be a
expression.
phase difference between the voltage and the inductor, and that is due to this part. See, when you are having a complex number, if it is a real number only, then real number into I will be in the same phase with V. Okay. But whenever there is some R plus j omega, then it gets multiplied with a complex number. So then it gives you that, if you draw it as a vector notation, you will see that V is basically Ri plus j omega L. J omega, since it is J, it is 90 degree with respect to your Ri. Okay. So Ri is in 0 phase. J omega L will be in this phase. Okay. And what is your V in that case? V will be the vector addition of these two. So there is a phase difference between I is in this direction. So I is in this direction, V will be in this direction. So there is a phase difference between the two.
So, sir, we are
Is it
using
clear?
this
I
imaginary
think
notation.
to some
For
extent,
phase.
isn't it? Huh?
Sir, we are using this imaginary notation for phase difference.
Phase difference, it is 90 degree phase.
Okay, sir.
That's why it's a complex, that's why we are saying it's like a complex number now. Because that in vector notation, we like it, write it like that. Okay.
Okay, sir.
Okay, so so j omega L will give you 90 degree phase shift with respect to R. And when you are combining these two, it will be somewhere in between 90 and 0 degree, because here it is added. Okay. Now, in this model, if you see, I don't have any capacitor along the line, because we assume that the capacitance effect is only along this. Okay. So that's why I have not included for capacitance. What will be the impedance offered by capacitance? It is 1 by j omega c. Again, if you remember, 1 by j omega c. So that will be minus 90 degree phase difference. Okay. But here I am not adding that, because we are not having that capacitor. We are assuming that capacitive effect is not along this line. Okay. Because capacitive effect, we consider it that capacitive effect is due to the parallel plate effect. These are all parasitic capacitance. There is no actual capacitance. Okay. So this parasitic capacitance, we assume that it is due to the parallel plate conductor. This is a one conductor, this is another conductor. They act like a parallel plate, and hence there will be a capacitance effect. So this capacitance is coming in parallel. Okay, it is a shunt capacitance. Okay, and hence the conductance, which is now the reciprocal of the resistance, is G. Okay, and the this capacitance, that gives a reactance equal to 1 by j omega c. So its inverse will be j omega c only. Okay, so this gives you the corresponding admittance. The word admittance is here, we use the word impedance. Okay, this is the word used for it. The reciprocal of impedance is called admittance. Is it clear? Someone was asking me. Admittance.
Yes, sir, it's clear.
So it is basically the reciprocal, the term used for reciprocal of impedance. As you use conductance as reciprocal of resistance, but here now it is not only conductance, you have the reciprocal of the reactance due to capacitance also. So that's why we are calling it now, it is the reciprocal of impedance, which is admittance. Okay. Okay. So these are basically the two equations basically governing how the voltage and the current will change. Okay, voltage and current will be changing with your as the current flows through the transmission line. This is the two equations. Now, if you just manipulate these two, I have just shown here. If you can see that if I manipulate these two equations, you will be having this double differentiation equation like this. d2v dx square will be equal to this. Okay, it will be equal to this, and taking gamma is equal to root over this, I can write this will be equal to gamma square v. Okay, similarly d2i dx square also comes out to be gamma square I. Okay, so you can see now I am having everything in the form of a differential equation, and now you see that this is the same type of equation we were having earlier in the wave equation. Okay, it is somewhat like your that oscillating wave equation. Okay, so the same similar wave equation we also have in our wave. Actually, that is what actually the target is. We want to show that the voltage and the current that flows in the conductor, they are also electromagnetic waves. They are also of the form of electromagnetic waves. That is basically the purpose of doing all this here. Otherwise, till now, when you were studying all current, electricity, everything flowing through the conductor, you never bothered about that whether this voltage and current, whether they are waveform or not, whether they are electromagnetic waves. We have never done that calculation. Okay, we have not looked into it mathematically. Now here, if you look into it mathematically, now you can see that basically your voltage Vt at any point x will be at any time t and at any time x is given by the solution of this differential equation, which gives you this, and the solution of this differential equation will give you this. These are basically the same type of, and since it is exponential of this, that can be expanded and you can write it in this form. Okay, it can be written in this form, which you can see, it is nothing but again that sine cosine term which we have used in our waveform equation. Okay, so it is basically, you can see that it is a combined effect of time and x. You know that in waveform equation also we have that at any point x, the waveform changes with respect to time. There will be some oscillation with the frequency omega, and there will be some change in phase due to x, and which basically gives you that the wave is propagating in the direction of x. This you have seen earlier, the similar equation for the wave. So basically V and I, it can be, if I do the solution of this differential equation, that also boils down to a waveform type equation. So
Excuse me, sir.
good.
Sir, how can we show that speed of current is speed of light?
Speed of current is speed of light. Okay, if you even if you take V instead of C, if you take V, then you will be having the same equation. Equation will come as, because you see here I have not used anywhere C. Okay, I have not used the voltage velocity anywhere. Okay, although I have used it here. I have mentioned it here because later on you will see. Later on when you will be doing the derivation, that time you will see that it will come out to be not exactly equal to C, but it will come near to C, where C is actually, C, you know, it is equal to 1 by root over mu into epsilon. Okay,
Yes,
that
sir.
we have studied earlier. Okay, now actually the velocity here is equal to 1 by root over mu into epsilon. Okay, so that mu and epsilon will actually matter. You are true. It may not be equal to C, but it will be very near to C. If that mu into epsilon is very near to mu naught and epsilon naught. And we assume in most of the good transmission lines, I am saying again, good transmission lines, the mu and epsilon are taken to be very nearer to the mu naught and epsilon naught. Then this velocity will be equal to C. Okay. Otherwise, as you are right, it may not be equal to, this velocity will be slightly smaller than C. That
Sir,
is
how
true.
mu and epsilon
Huh?
can be equal to mu naught and epsilon naught? They
No,
are of
it
free
will
space
not
and
equal. I am again saying I am not. It is not equal. It is not equal. Then it will be it will be different. It will be different.
okay, sir.
I have just written it here just because I am taking it, assuming that it is quite close to C. Okay.
Okay.
Otherwise, see, later on I have never used it. I have just written it here as equal to C. In fact, you can write it as V also. Okay, if you are not satisfied, you can write it as V. Okay, but it is generally very close to C. Okay, I'm assuming it here that it is equal to C. I'm just assuming it. Okay, because
And sir,
there is
this
slight difference, not
okay, sir.
much. Okay, not much. It will be, there will be a slight difference, but very close to C. Okay.
Yes, sir.
Otherwise, you see, I have not used anywhere. I have here. You are not seeing anything. I have not used anywhere this C. Okay. Okay.
Yes, sir. And sir, this
That is
lambda is
just an
de
assumption.
Broglie wavelength.
Uh, That is just an assumption that the velocity is very much close. Okay. It is very much close to your thing. Okay.
Yes, sir. And sir, I was asking that lambda was de Broglie wavelength or
This
something else.
no, that
Like,
lambda is just your wavelength of the transmission. X
so what will
lambda
be
is
wavelength
equal
of
to your
electron?
velocity, na? Wave velocity.
No, sir, like in transmission line, like current is flowing. So how can we define wavelength
Which
for
one?
the current?
Current. See, it is the current is not a DC current. It is not a DC current anymore. We are talking about. And so even the current that is transmitted at your home, AC current, that is having 50 hertz. 50 hertz frequency. I'm
Yes,
not
sir.
talking about any DC. DC will have if f will be equal to 0. There the frequency becomes 0. Okay. So I'm talking about alternating current, alternating voltage, which will be having some frequency. And in fact, now we are actually talking about whether it is possible to transmit any high frequency wave. Okay. At your home, you have the conductor carrying only just 50 hertz, which is very small frequency. Okay. But when we are talking about transmission line, then we design the conductors in such a way. That's why I said that just simple conductor, simple copper wire cannot carry high frequency. Okay. We design it so that it is carrying some high frequency F. So it will be having some F, some lambda, and F into lambda will be equal to your velocity. And that velocity I am saying will be quite close to your C. Okay. So that is how the transmission line has to be designed. Okay.
Yes,
Okay.
sir. And sir, can you explain this balanced and unbalanced line again?
Balanced line is just if you see this picture. This here balanced line means this will be plus B, this will be minus B. Okay. So with respect to the ground, you can say they are symmetric. Okay. With respect to a ground, some ground is 0, we always consider. So this is plus B, this is minus B. Okay. Whereas in other cases, it is plus B, but there is no minus B. The other line is the ground itself. Okay. So these are all unbalanced lines. Here also it is unbalanced. Okay. So that's why in coaxial cable, actually it is plus B minus B, but the problem is here actually the electric field is not with respect to the ground. The electric field will be, say, if this is plus B, the electric field will be from plus B to minus B. Okay. Whereas here actually the electric field will be with respect to your ground. That's why it is called a balanced line. Okay. Here it will be an electric field with respect to the ground, and here the electric field will be with respect to the ground again. Okay. But here there will be an electric field with respect to this with the ground, but this one will not have any electric field with respect to the ground. That's why it is unbalanced here. Okay. Because the it is enclosed inside, so it cannot have any electric field formed with respect to the ground. But this one will, the outside conductor will have one electric field formed with respect to the ground. That's why it is now unbalanced. Okay. Inside one is not having any electric field formed with the ground, but the outside one will have one electric field formed with the ground. So that's why it is unbalanced. Okay. So that symmetry should be there. Means both the conductors should have a symmetry. Here you can have that, but here you will not have that. Here you will not have that. That unsymmetric, there becomes asymmetry. That's why it is unbalanced. Okay.
Okay, sir.
So I think just let me see what else is there. Okay, I'll just finish up with this slide. Okay, I think then we'll talk about the other slides in the next class. So as I said, basically for if you solve these two equations, you will get something like that wave equations again. Okay, because the same thing you have done in wave equations also. There you solve the differential equation and you get the similar equations, and that is wave equations. Here one thing you just see that I have one V plus and V minus. Actually mathematically you should have this. Okay, you will be having two components. Okay, so we are not going into details right now. This derivation and all those things you will be studying afterwards in your microwave engineering. So there you will see that actually at every point you will be having two components of the waveform. Maybe in physics you have studied this. I don't know whether you have studied that. There will be two components. One is called the forwarding wave. The other one is called the backward wave. Okay, I don't know. In physics you might have studied it. In physics,
No, sir.
Okay, then in microwave engineering you will study it. Otherwise, in physics also people, when they talk about the waveform and all these things, electromagnetic waves, they teach this. That this waveform is having two parts, basically the forward traveling wave and the backward traveling wave. Okay, actually that forms we'll study it later on. that this forwarding and the backward traveling wave, there is a reflection back. That's why that backward traveling wave will be there. This reflection will be from the load. There will be a reflection. And because of that, some standing wave pattern, something called standing wave pattern, that also is formed. Okay. So this backward traveling wave is actually due to some reflection back from the load. It will happen. Okay. So anyway, right now just take it for granted. We are not going into details of that. So there is the forward traveling wave, the backward traveling wave at any point as given by this equation. This is the forward traveling wave part. This is the backward traveling wave part. Okay. Then as I have written here, that this gamma can be expanded in the form of alpha plus j beta, because this is a complex number. So it can be written in this form. And as you can see that this alpha and beta, alpha is coming as e to the power minus alpha x. So this alpha is a real part. So accordingly, the voltage actually will be decaying with x, with the distance. As you travel, it will be decaying. Okay, it will keep on exponentially dying out, the voltage amplitude. So that is the decaying factor alpha. Okay, and you can see here that this beta is actually responsible. The beta is responsible in both the cases. The beta is responsible for your phase change. Okay, and your phase will change obviously after every lambda. After every lambda distance, this phase change will be 2 pi. So beta should be equal to 2 pi by lambda. Okay, beta should be equal to 2 pi by lambda, and this beta is called the phase constant. Alpha is called the attenuation constant because it is responsible for your exponential decay in your wave. Okay, what are their units? As you can understand here, beta is nothing but the unit should be in radian per meter. Okay, because beta into x gives you a change in phase given in radian. Okay, so that's why the unit is radian per meter. This alpha, it is something new. The unit is something new. It gives you actually exponential decay, and the unit is written in terms of Nepar per meter. Okay, the unit is given like that. Okay, Nepar per meter. Later on in your second year, you will encounter again this term Nepar. Okay, when you will be studying Laplace transform, that time you will be encountering this term again, Nepar. Okay, so this is actually the Nepar is the rate of decay, exponential decay. Okay, the unit for that is given as Nepar. Okay, so in this equation, just these two things you have to know basically, that there is an attenuation constant. So accordingly, there will be an exponential decay, and there is also a phase constant due to which with distance there will be a phase change, and hence the waveform is formed. That is why the waveform is actually propagated. Now you can see here, I have shown that the exponentially how the amplitude is decaying, and how the phase change is there with distance, and that is which actually gives you, and you know that with time there will be this omega t, that oscillation is there at every point, there will be oscillation, and that is how the waveform is formed. This is how the waveform. So there is a change in the waveform that you have seen earlier. There we have not talked about the change in the amplitude. We have only said that there will be change in phase with distance, and with time there will be oscillation. That is what we have said earlier. But now we have introduced here in this transmission line that there will be some decay exponentially, and that is why you can see that due to this attenuation, we will not like to have high frequency transmission over a transmission line. because transmission line actually gives you this problem, this attenuation. Okay. In fact, this one will also give you that your wireless medium also gives you attenuation, but in transmission line it becomes very prominent at high frequency. Okay, that will
Sir?
again. Bolo.
Sir, if high frequency causes loss, then why DC current gives more loss?
DC current gives you more loss.
Like if we make frequency 0, then by this theory we should have no loss, but DC current
That
gives
is
more
a
loss.
different thing. That is basically the ohmic loss. That is because the ohmic loss means that is because of the ohms drop. Okay. Here it is a different case. Here you can see, I'll just show you. Here this is because of this j omega L. It is because of this j omega L. In DC, you don't have that component. Okay, in DC you don't have this component. Okay, you don't have this component j omega c. In DC you will be not having. There it is only R and G. Okay, there is no inductance, no capacitive effect. Here it is coming due to this inductive and capacitive effect. Okay, that is creating the problem here. Okay, here the problem is created by this L and the C. The inductor that is inductance offered by the conductance and the capacitance offered by the conductance, offered by the conductor. Okay, that is actually creating the problem here. It is the problem created by these two factors, L and C. Okay, whereas in the DC transmission there this R and G, because in DC transmission I am not bothered, there is nothing to do with L and C. They will not affect anything. It is basically the ohmic drop due to R. Okay, resistance only. Here the problem is actually coming due to this ohmic. Okay, due to this ohmic. Okay, so that's why you have to have, we will do this transmission. It's not that we are not doing high frequency transmission here. We are going for high frequency transmission. We are going for it. Okay, but we have to design it in such a way that this L and C, they should matter less. Okay, they should not create too much of problem. Okay, this impedance due to L, the impedance due to C, that should be minimized. Okay, because omega is high. So when omega is becoming higher and higher, then we have to design in such a way that this L and C, we have to make it smaller and smaller. If we make L and C smaller and smaller, then this omega, when it is increased, then you will be having less problem. Okay. So accordingly, the conductor has to be taken. Okay, the conducting line has to be taken. That's why gradually we'll go from transmission line, we'll go to the waveguide, and then we'll go to the free space transmission, where L and C effect will be less and less, so that omega can be increased, but L and C, since they are smaller and smaller, the effect will be reduced. Overall effect of omega L, overall effect of omega C will be reduced. Okay, that is what actually we are concerned about. Okay, because what you are talking about is the R and G part. Now this R and G part has nothing to do with my frequency. Okay, that is for a DC, it will offer some R. So when you are having DC, RI will obviously come, R into I, G into V, that will come. Okay, and we will try to have a less drop, ohmic drop. So this is called the ohmic drop. It gives you Ohm's law. According to the Ohm's law, whatever drop is there. Okay. Bolo. Any more question? So if not, then we will continue in the next class. Okay, we have basically completed the transmission line. Okay, next class we will continue from the waveguides. Just one more slide is there on transmission length, then we'll talk about waveguides in the next class. Okay. Chalo.
Thank you, sir.
Okay.
Thank you, sir.
So
Thank you, sir.
we'll meet again on Monday. So you can, I think now you can leave the meeting if you are not having any question. Okay. Sure.
Thank you, sir.
Thank you, sir.
Okay. Bye, all of you.